So folks, I just want to give you a video overview of the solution that I've written out for this. Here we've got a function f of x, y, and it's stated here, and we want to find the linear approximation of f at the point -1 to 1. Really what we mean is at the domain value, the order pair -1, 2. So here's the formula for the linear approximation, and it should look familiar. It's just one of our forms of the equation of the tangent plane on the right. On the left-hand side, we just refer to it as a linear approximation as opposed to a tangent plane. So again, we got that formula looking up above here from right here. That's where we get that formula. And I really consider these sort of plug and chug problems. So the first thing we're going to do is compute f of -1, 2. I did that, I got 1. Then I found the partial derivative of f with respect to x. Notice that to do that, I had to do the quotient rule. I guess I could have rewritten this as 5 times x squared plus y squared all to the -1 power and done a chain rule. That would have been fine. But I went ahead and did the quotient rule on that. Then I evaluated the partial derivative of f with respect to x at the point of interest. That gave me 2/5. So all of that is going to tell me what to plug into this part right here of the formula. Likewise, I computed the partial derivative with respect to y, and then I evaluated that at the point -1, 2, and that gave me the number -4/5. So now I construct the linearization, and I don't know why that just moved on me. The linearization, and I like to do this, folks. The book doesn't do this, and most people don't, but I like to say where I've anchored the linearization at. It reminds me of where that point was of x, y, and there it is. It's just simply f's of x at that point, f's of y at that point, and there we have x minus the a value, y minus the b value, and then 1 we got when we evaluated -1, 2 at this point. So again, folks, I don't think there's a lot to this. It's just plugging things into this formula. So the next question says, why would we come up with a linear approximation other than to approximate other points on the function? So notice that the point that we're asking to approximate here is this order pair -1.05, 2.1. Now that's meaningful because it's close to our anchor point that we started with. So there's our answer from the previous part. And then what I do is I simply if I want to know what the z value is going to be on that function, a good enough approximation is to say, well, what would the z value be on the tangent plane at that point? And so I went ahead and plugged this point into our linear approximation here, and I got an answer of 0.90. Now, just to compare that, the true answer to that problem is about 0.901, or we're within 1/100th of the true answer with our approximation. So the next thing I did is you'll see on your version of this, there's a place to click for a CalcPlot 3D. Let's see here, pulling that over. Here's where we can click the CalcPlot 3D. So actually, before we go to CalcPlot 3D, let's first download the script. So you click on this link here. It'll take you to the Dropbox file of the script. As a reminder, you need to directly download this script. It saves it to your file. Wherever you've saved it, then you're going to go click on the link to CalcPlot 3D. So we click on that link to CalcPlot 3D, and then we're going to go load that script. So we'll click on Load Script, and we'll load that script that we just downloaded wherever you saved it. So here's the script, and unfortunately I want to change a couple things to make it easier to see, and it just won't save these. So I'm going to go click on the plane where z is equal to 0, and I don't want those edges on there. I want to make this a little bit easier on the eyes. So here you can see in this transparent red, you see the graph of our function. That's this z equals 5 divided by x squared plus y squared. There it is. Here you can see the point in the domain where we're going to build our linearization about, which corresponds to this order triplet on the graph of the function. So the whole idea is that we want to take some other point. In this case, the order pair negative, so I don't know if you can see that, there's that -1.05, 2.1, that's this point right here on the graph shown in blue in the domain, and we want to know, okay, if we were to plug that point into the function, that's going to give us some other point, but the thing is we don't know, hopefully you can see the question mark on there, we don't know what that z-coordinate is on the graph of the function. So what's our strategy? Well, our strategy is to go ahead and, rather than working with the function, to construct the tangent plane at that point, the original point P, and that's where we're going to anchor this linearization about. So let me go ahead and turn on the tangent plane by clicking this here, but now we've got sort of a mess. So I'm going to do two things with that tangent plane. The first, or two things, I'm going to first change this to hide the edges. That would make that a little easier to see. So now we've just got this, now it doesn't have all the coordinates. And then the next thing I'm going to ask it to do is, let's go back to the graph of the function and let's get rid of the color. So we'll just do the wireframe only. So now you can see that we've taken our point P and we've constructed this blue tangent plane about it. And the whole point is now we want to use this to approximate this particular z value. So the next thing I want to do is, because it's kind of hard to see what's going on here, is let's go ahead and zoom way in on this thing. So I'm going to zoom way in on that point. So let's see here. I'll click here and I'll zoom in on by a factor of 20 into each of those coordinates. And here you can see, hopefully you can kind of see this. There's the point P where we've constructed the tangent plane at. Here's the point Q, and it's hard to tell. That point Q does not lie on the tangent plane. It instead lies on the function itself. If we were to plug the ordered pair negative 1.05, 2.1 into our linearization, that gives us this green point right here. And you can see that that green point does indeed lie on the tangent plane, and its z-coordinate is 0.9, which is very close to the z-coordinate of the point Q that we were after. Remember that the actual coordinate for that point Q is about 0.9 or 0.907 or so was what that was. And so that's what I mean by using the tangent plane to approximate a point on a curve. And that's what we do in this process of linearization. Zoom in on that a little bit. So hopefully that gives you kind of an overview of what we mean by linearization. It's not essential that you have a picture going along with this each time, but I do think it's important to realize that what we do when we build this linearization function is we're constructing the equation of a tangent plane or a hypertangent plane, depending on the number of variables we have, but we're constructing the equation of a tangent plane and we're using that to approximate values on the function. And when we plug in the ordered pair negative 1.05, 2.1, which is close to where we've anchored this thing at, we get a z value that is close to the actual z value of the function. Anyway, folks, I hope this was illuminating. It's not the most, I find it not the most interesting of topics because it's kind of plug and chug. Let me know what your questions are, though, as you're working the homework.